I'm very glad to be present in this conference with you people. Now, I'm a professor in Indian Institute of Technology, Kharagpur, India, and I'm the faculty member of this department and in the institute since 1997. Now, previously, within that I was the faculty member in the School of Management, but now I'm the faculty member in the Department of Mathematics. But I studied here itself, and I started my research in fuzzy logic when I joined as PhD student here itself. This is my parent department rather, and since then I am working on this. I'm very fond of doing work on fuzzy logic. Being a mathematician, I started my journey in the area of optimization, but later on I will say what is the origin of my thinking for fuzzy plane geometry. Now I just deviated my research works little bit on fuzzy plane geometry, and my students are doing PhD on that part. Even I published book even on the topic. If you feel interested, then you can see that. But I like to do work on this topic. That's why I thought let me share my idea, my origin of thinking, and the genesis of my work in this forum. Now, today's topic is the application of fuzzy plane geometry in multi-criteria decision making. Now, this is a kind of optimization problem, and we are dealing with the decision making situation. For any decision making situation, we are having 4 steps. First step is the information acquisition, that is the gathering of information for the decision making situation. Second is the quantification of information. Third is the simulation, and fourth is the decision in this sequel. Now, identifying the goal of the decision making is the primary task for any decision making situation. If my goal is not fixed, then if my goal is rather not pinpointed, then we will away from reality. That is the idea for any decision situation. Now, but in general, what is happening while we are making the decision, that time it happens that our objective is not one. For example, I'm having certain budget with me, and with that budget, I have to purchase many things together. I cannot satisfy myself to purchase everything at the fullest satisfaction. I have to compromise somewhere. I have to reduce the amount for one thing in lieu of the other object. That is happening all the time without knowing multi-criteria decision making. We apply our common sense and just try to reach at our goal at the best. Now, but it may happen the information, whatever we are gathering from the situation, those information is not always very precise in nature. Now, since this conference is solely devoted on fuzzy logic, and there are very few in a year people are doing conference on fuzzy logic, devoting on the whole concentration on fuzzy logic. That's why I feel all the participants and all of you are very well acquainted of the fuzzy environment. That's why I need not to say why fuzzy is needed. Rather, I would say if the environment is imprecise in nature, in that case, collection of information in a imprecise event in imprecise environment is not so easy, because either the information is a qualitative or it may the quantitative or the combination of both. That's why decision making in fuzzy environment is really a challenge for us. Let me just you just consider a simple mathematical example that we want to maximize a function. Function is only the single variable x, where x is less than equal to 11. Now you see, this is so simple that if I want to maximize x within the area of x less than equal to 11, then I will reach in this simple geometry. That is, x equal to 11 is the red line, and x less than equal to 11 is the area below to it, x equal to 11, and my decision is y equal to x. That's why if y-axis is my objective function, simply it would be the blue line. That's why if I just see what is the solution, then very nicely we can say that would be the intersection of the objective function and the constraint point, and certainly it's x equal to 11. There is no doubt about it. Even without knowing geometry, even you can solve it. Okay, now the situation is becoming little difficult. If we reframe the problem in such a manner that obtain a value of x substantially larger than 10, while making sure the maximum value of x should be in the vicinity of 11. Now you see, so many changes are there in the expression rather the information here. Here also we can take maximize x, and x must be in the near to 11. But you see, if I just approximate the situation, then I would be far from reality. That's why in information technology, it has been always said, gather more information as you can, because if you do not consider the information fully, it may happen that we will be away from reality. Now, you see, in this situation, let us just try to work with the linguistic value that a value of x substantially larger than 10, that's one part, and it must be in the vicinity of 11. Therefore, the thing is coming as the computation with words. Nowadays, people are working on the natural language processing. Use the machine learning technique and other thing, but fuzzy logic is such a nice thing. Very nicely we can just mathematize, quantify the statement that x is substantially larger than 10. Hope you could understand. Just to look at the graph, if x is equal to 10, lesser than 10, then I am not happy. If I just draw my curve of happiness here, then it would be from 10 to 12 point something. My happiness is increasing, and after 12.5 I'm quite happy, and my satisfaction level is same as such. That's why with the red graph we can explain how x is substantially larger than 10. Now, if x is substantially larger than 10 with the membership function, I need not to say the definition of membership function at all, because you all know what is the membership function. Therefore, we can just say that this is a mathematical function, a nonlinear function, and with which we can approximate this red curve. And you see here also that if x equal to 10, the value is 0. And beyond 10, the value is increasing further and further. And beyond certain point, value will converge to 1. Okay, that is the idea. Now, another statement was there. Maximum value of x should be in the vicinity of 11. Therefore, in the vicinity of 11, I can just draw another curve. I would say if it is 11, I'm quite satisfied. If it is lesser than 11, up to 8 point, in the lower level up to 8 point something, I can tolerate my statement that in the vicinity of 11. Beyond 13, I can just be happy. I'm not happy. Up to 13, I can tolerate. Then I can draw my level of satisfaction this way. And that could be the membership function. You know, for decision making problem, as I showed you before, when there is no fuzziness, generally the solution would be the intersection of the objective function, that maximum value should be at the vicinity of 11. That's my objective function. And what is the constraint? Constraint is x substantially larger than 10. Therefore, that would be the intersection of these two. Now, intersection of these two, just here I mean to say that in the vicinity of 11, though we have done with the nonlinear membership function here, that totally depends on my perception, my way of thinking. The vicinity of 11, instead of nonlinear, we can just approximate with linear one as well. That much I just wanted to say. But the solution would be intersection of these two curves. And you could see we want to maximize the intersection area. Therefore, the solution would be at x equal to 11.75. Now, it can be said, this is the principle by Bellman and Jardhe, that any decision making problem can be just checked. We can consider as a intersecting region, and we will apply the max min operator there. And with this max min operator, min is the intersecting of 2 and max would be the maximum value with the intersecting region. So we are getting 11.75. Now you could see that the situation from 11 to it's coming 11.75. Therefore, if I could have approximated the whole thing, but I would be away from the reality. Now you see here, computation of words are very an imprecise environment, because words are less precise than numbers. And so computing with words is less precise than computing with numbers. But in this, it serves to measure purposes. When precise information is not available, we can do very nicely. And if the precise information is available, like in the vicinity of 11, but there is a tolerance for imprecision, that also we can just capture and we can include it. Let us consider a very simple example in a multi-criteria decision making, where we have several objective functions together. Now, here company desires to select a suitable city for establishing a new distribution center, and the evaluation is done according to the investment cost and the closeness to the demand market. Now, the data is given in the next, but here my objective is that investment cost must be minimum and it must be close to the demand market. Now, you see, this is the data. There are the alternatives are A, B, C, D, E. These are my decision space only alternatives, but the investment cost in the individual cities are given in this manner: 10, 9, fuzzy 10, fuzzy 9, fuzzy 8, like that. And the closeness to demand market as well, some other value. Can you identify a single one which is the best one? Really, we cannot, because, for example, though the closeness is the minimum at the city A, 5.7, around 5.7, but here you see the investment cost is maximum 10. We won't get any option where both the things are minimum. Therefore, the concept of multi-criteria decision making is there. And you see, very nicely we can just draw the options. In the x-axis, we put the closeness to demand market. In the y-axis, the investment cost in crores. You see the options are A, B, C, D, E. Could you see the option A here, we are having now. Could you see that options are having as? Am I audible to everybody?
Yes, Professor, you're audible.
Okay, thank you. Now, you see, the option, just I was saying that fuzzy numbers, if we just plot a fuzzy number in x-axis and fuzzy number in y-axis, we will get a hazy region in the xy plane. Therefore, my option A would be a fuzzy point, you see. Similarly for B, C, D, E. Now the question comes, how to compare? Here you see, we won't get any total ordering. This is the partial ordering. This is the first challenge. And the second challenge is that whenever you are having this hazy area, that means that would be the collection of many points together in A. Now, here the membership function only differ in different ponds. Therefore, comparison is in another challenging task for us. But for multi-criteria, you could say we can prove it. We can show you, we can show the logic how to get uh, the the solution for it. In multi-criteria, generally we don't have any optimal solution. Rather, we are considering the Pareto optimality. That is the main thing in multi-criteria decision making. And here the solution is that we can conclude from certain situation that the B is dominated by C because C is the better than B. Similarly, D is better, C is worse than E, and A is better than B, but we cannot compare the options A and C together. That's why we can say A, C, and E all are equally acceptable. Similarly, B and D are equally acceptable, but both the combinations B and D are worse than the combinations of A, C, and E. That's why we can have different Pareto front. As you know, in genetic algorithm, also in multi-criteria decision making, we do the same. We are getting different Pareto fronts in the decision space. Now, this could be, the situation could be more complicated if we have more number of objectives. You see, we are trying to find out our option for a certain car model, but there the price of car consumption and the power, they differ. But we want, the target is the less price, more power, and the less petrol consumption. That is, we want better mileage altogether. Finding out a solution is again a difficult task here. That's why in multi-criteria decision making, I could say that we are having multiple objectives, conflicting criteria, incommensurable units. That means attributes and the objectives are measured in a different scale, and we have to design the whole situation. That is the problem for us. And generally, if this is if we consider that in the x-axis the one function and in the y-axis another function, then we can say the Pareto front. I'm not going into detail about the definition of Pareto optimality. I would give the overview of the everything. I could say the region from A to B is the Pareto optimal frontier when the environment is precise in nature. But if the environment is imprecise, whole feasible space is imprecise, you see, and getting the Pareto front is again a difficult task because that would be the region that is the hazy curve. And Zade has said in, in 2009 that if we draw with a spray pen on a paper, whatever region would be generated for drawing a curve, that would be the fuzzy curve for us. Therefore, fuzzy curve, I could say, identifying the points again here would be very difficult. This is another situation where we're having two objectives, but rather the decision space is three-dimensional. All right. Now, in that case, from decision space, if we just go to the objective function space, for precise multi-objective, it looks like this. For imprecise, it will look something different. Okay, you see, the region is very hazy, the boundary, and always, you know, optimal solutions. Rather, the Pareto optimal solution for multi-criteria always is at the boundary of the space. Therefore, finding out boundary, I will give you few examples from here. Just simple examples I have taken. Say minimize x square and minimize x minus 2 square, where the coefficients are fuzzy numbers 1 and 1. We can take the triangular fuzzy numbers even. If we draw the curves, you see the curves are fuzzy. The middle line is the curve where the membership function is 1, and the other two curves are the membership function 0. That way, if we just draw, you see the intersecting region is a point. Rather, I would say this is a set, fuzzy set altogether. Now, if I just take another example, here also you see the constraint, both the objective functions, rather constraint is not there, unconstrained optimization problem. And here also the same thing we are getting, that the region is very much hazy in nature. Finding out the para-optimal solution would be really difficult. From here, our journey started and we thought how to capture the para to front, which is very much hazy in nature. Now, you see, if it is hazy in nature, I could say if this is a fuzzy curve, any curve is the collection of points. Now, precise curve is the collection of normal points where two coordinates are there very precisely. But if the curve is fuzzy, then that would be the collection, must be the collection of fuzzy points. From here, our journey started and we wanted to see what is the definition of fuzzy point. And we could see there is hardly, that was a very less works in 2007, very less works were there. Till date, there is not much work on fuzzy geometry. And only two authors, Buckley and Islami, they have defined the fuzzy point. And we started our journey from here. And this is the literature. I'm not going into detail about it. Just I will show you the theory behind that, how to construct the fuzzy point, because for any geometry, point is the primary building block for any geometry. Now you could understand how fuzzy point concept has come in optimization context, because point is something that is the unit for the line, unit for the circle, for conic section, and for everything. That's why while we started journey, we started the thinking about a point. Then we connected 2 points. We declared that word, that is a line, fuzzy line. Then we defined circle, triangle, conics, and we just found different thing. The cross section of two lines, fuzzy lines, and perpendicular on a fuzzy line. You could understand if the hazy lines are there, then the cross section would be again a hazy point. That's why we started thinking. As I was saying, the Jadhe said about the definition about the fuzzy curve. Just if you draw with a spray pen, then fuzzy transform of that curve would be the fuzzy curve, he said. And that would thus, now you see how it looks like in a region. This is my fuzzy point. Okay, in x-axis and y-axis, if we just draw, now you see we are getting a collection of points with varied membership value. And in the right, in the z-axis, if we put the membership function, you could see it would be, though it's look like a right circular cone, but still the membership function. But you see the in the x-axis, whatever point is there, that's a fuzzy point altogether. All right. Now, this is the membership function, etc. In the journey, we had to define fuzzy number along any line in the space, because we know fuzzy number is only the on the real line. But for defining any point, because we thought any point is the collection of fuzzy numbers rather in different directions. And we defined many things, like we defined the fuzzy number along a line, we define fuzzy point, and here the same point, inverse point concepts, all we have done, and we try to draw the fuzzy line. You see, this is the proposal by Buckley and Islami, that if the number fuzzy points P1, P2, P3 are there, they said that you collect all the points as many ways you can. But when we connected it, we could see the whole region is just diverged beyond P3 and below P1. Do you think ultimately it will form a line? It will form, there is a butterfly effect beyond P3 and below P1. Then we thought maybe there is something mistake is there. Then we thought this, how, and always it has been said, whatever definition you do for fuzzy, that must be customarily we can scale down for the classical definition. Otherwise, inner conformity will miss, and we cannot declare this is a fuzzy concept at all. That's why we thought how we can define it. Then we started the journey by connecting all fuzzy numbers together. And here we have used certain theory given by Doba and Prade, and there we could connect. We didn't connect A1 with B1. Rather, we have connected A1 with another point. Just you see, we connected this way, that lower with the lower and upper with the upper in the fuzzy number, which has been given, the idea has been given by Dubai Pradi. We just implemented that one in geometry. Now, with the extension principle, very nicely we could draw. And another best part of it that you see, the information for P2 was missing for Buckley and Islami, but for our case, all the information we could gather very nicely. Then this is a line segment rather, because we connected P1 and P3. Then our journey started. If we just want to get the fuzzy line where the line segment will be infinitely extended, how it looks like, you see, there are different points with different membership value, membership pattern rather. P1, P2 is the diamond shape membership function, P3, P4, and P5. With the idea I showed you before, which we have developed, we could draw a very nice fuzzy line. Not only that, we can give the equation of this line. There is a mathematics behind it. All right. Now, in this way, we just thought to extend, and we defined fuzzy circle when the radius is a fuzzy number, center is a fuzzy number, and if the center is not fuzzy, etc., there also we could get, and the fuzzy circle may look like this. Now, if we do not develop the conic sections and other thing, how we can apply in our just in our multi-criteria decision making. That's why still we are working on it. I could say hopefully my time is over, because it's only 30 minutes over. Am I right? Is that okay? Now, I just wanted to just summarize my lecture with something. We applied it in an application, that is the lung cancer application. We have taken data for 22 patients, and we collected information from the CT scan and from other histopathological. I work with the medical scientists. I collaborate with them, and you see, we could see that lung cancer, this is generated from a lesion, that is a growth in lung. And if the lesion, that is the tumor, that is the growth in lung, is having certain properties, then only it is approaching to cancer. Otherwise it may be benign. That's why we collected information for 22 patients about the lesion size, lesion margin, internal attenuation, cavitation, satellite lesion, and there are many more we considered. I have just took few here, and with that we applied our developed theory, and we could see from the data, and this is the theory. We could say that we wanted to just map the patient's condition based on those criteria, because that is again a multi-criteria application between 0 to 1. If it is 0, it is benign but infective. If it is 1, that is fully malignant. That's why in between, the grade of membership value between 0 to 1 gives us the scale of malignancy. In that way, we applied our theory there, and we could see the range, and whatever doctor's impressions, we have collected that as well, and we could see that it's very much matching with our score with the doctor's impression. Now still we are working on the oral cancer and other thing. Being a mathematician, I can only contribute on the theoretical part. That's why still my journey is on. I have a team with mathematicians and with a medical scientist. Hopefully we can do something on this area. Now, really thank you for listening to me.